Hello everybody, my name is Iqbal Khan. I'm the technology evangelist at Alachisoft. Today I'm going to talk about how to scale .NET applications with distributed caching. But before I get started, I want to just give you a quick introduction to who we are. So our company is a San Francisco Bay Area based company called Alachisoft. And our flagship product is NCache. It's a .NET distributed cache. It's an open source, Apache 2.0 open source product. We also have a product in Java which does the same thing as NCache called CaseGrid, and that's also an open source product. We've been in this space for the last 10 years. NCache was launched in 2005 and is used quite extensively all over the world. I'll talk about that more toward the end, but this talk is more about a specific problem that a lot of people are facing these days, which is the application scalability, and how to make sure that your application performance stays really good even under peak loads. So I prefer to keep the discussion more interactive, so please ask me questions as and when you have them, so that we can have a more discussion-oriented talk. So I'm going to go through a few definitions. I'm sure you know these already, but just for clarification purposes. The first is, what is scalability? Scalability is the high application performance under peak loads. So if you have an application with only 5 users and your performance is bad, that means your performance is bad. I mean, that doesn't matter whether you have 5 users or 5,000 users, your application just does not perform. So you try to make sure that your application response time is good, you don't have any application logic issues, and your response time, in case of an ASP.NET application, is usually under 3 seconds. So that is called good performance. But if you go from 5 users to 5,000 users or 50,000 users, if the performance was good with 5 users, but it was no longer good as you increase load, that means your application is not scalable. And it means that even though your performance was good, you had good application logic, you didn't architect the application for scalability. So today, without having this goal met, many people will have problems in the application that they develop. So that is the definition of scalability. Another definition, what is linear scalability? So most of the server applications today are either web applications or web services or other server applications. They run in a multi-server environment. And you normally have a load balancer in front of this application server pool, which directs traffic evenly to all of the servers. If you have an entire application infrastructure where as you add more servers, the transaction capacity is increasing in a linear fashion, you have a linear scalability. And if you do, your application is scalable. You don't have to worry about those peak seasons or peak times when maybe your traffic will double or triple, because you can just add more servers. That is one of the reasons the cloud computing is so popular, because places like Amazon or Azure allow you to easily add more servers to the application here. So linear scalability means that, and if you're not able to achieve linear scalability, that means that as you add more servers, the incremental benefit or the incremental transaction gain is not the same as it was in the last time you added. That means it's not linear. It's probably a logarithmic curve in that case. The third thing to keep in mind is what applications need scalability. Which ones actually need scalability? So if you have a web application, ASP.NET in case of .NET, Java server pages or JSP for Java, and so that is the most common case where application needs scalability. The other is, of course, web services. If you have a service-oriented architecture, SOA, you will need scalability in the same fashion that you will need for web applications. The only difference is that in case of web applications, the nature of the application is more human-oriented. So you have a concept of a session and others. which is not the case with web services because it's more of a web methods. Because your users are themselves the applications. The third types of applications are basically the back end that you are developing for Internet of Things, which is a very big movement these days. Devices are becoming smart and they're talking to a back end of some sort. And as you have a mushrooming of these devices, the back ends need to be able to scale because they have tens of thousands, if not hundreds of thousands, if not millions of these devices are talking to them. So the same way, most of these Internet of Things backends are usually web services type of a backend. The fourth use case is also becoming very popular, especially on the Java side. On the .NET side, we're not seeing a lot of activity yet, but it's going to come in the near future, which is if you are dealing with big data, data that you cannot process in one server. You cannot process in a relational database. You have to distribute it. And you distribute it because you need to scale. You need to be able to handle that much data in a reasonably short amount of time because marketing or your business needs to be able to analyze it to make intelligent decisions. So big data processing is another very emerging use case for scalability. And on the Java side, of course, Hadoop is a big name in this. And any other server applications, these that don't fit in that specific criteria. You have a lot of, especially the financial services industry, and even others, where they have server applications that are processing a lot of requests. So these are the types of applications. If you are doing any one of these, then you've come to the right talk. If you're not in these, then it's probably good to learn anyway. So what is the problem? Why are we even talking about this here today? The first thing is that the application tier scales in a very linear fashion. So if you have a web application, you can keep adding more servers, perfect, no problem at all. So the problem is with the data storage, because the data storage cannot scale in the same fashion as your application tier. You can have a 50 server web farm to handle that traffic, which in case of, for example, Ryanair, which is a customer of ours using NCache, they do have that size, maybe even more now. But you cannot have 50 servers in the database, or proportionally. Your relational databases are not designed to scale in the same fashion. That is why the NoSQL movement started. And that's why there's a lot of activity happening on the storage side to try to provide scalability, because this is the bottleneck. This is the reason why your applications are not scaling. If you architect your application correctly, you have good performance under not heavy load, you will not have scalability because the database is the one that's going to kill you. So the question then is NoSQL the answer? Yes, in some cases. If you can move away from relational, yes. But what we found is that the majority of the business applications, these are the web applications, the e-commerce applications, the online business applications, they need to stick to their traditional databases because there's a lot of other dependencies, and they're just not ready to move away from relational databases into a NoSQL. There's also some technical reasons. Relational has an ecosystem that you cannot yet substitute with NoSQL. So NoSQL is a great technology. We're also working on it, actually. We're going to be coming out with a NoSQL database product soon. But it is not a substitute for relational databases. So if you have situations where you must use relational databases, you cannot just say, I'm going to move to NoSQL. You may be able to move some of your data, but if bulk of your really active data, your customers, your accounts, your activities are still on relational or on the legacy mainframe, then, as they say, the strength of any chain is its weakest link. So you may have the greatest NoSQL, you may have the greatest application tier, but it's where the bottleneck is, that's what kills you. So this is clearly not an answer in a majority of the cases. So, and if you see the problem, as I explained, you've got the application tier scaling. You have the load balancer here, and these are the different types of storage. You have the application data, you have the extension storage in case of ASP.NET or web application, and you have the legacy. And these are the places that become the bottleneck. So the answer to that is to use distributed cache, an in-memory distributed cache. NCache, of course, is our flagship product that does that. But an in-memory distributed cache is faster and it's more scalable than your database. And the really nice thing about this is that you can use it with this right here, that blue, with your relational database. It does not require you to move away from your relational databases. And that's the real benefit of using a distributed cache is that you can continue to use your relational databases that would otherwise kill you if you didn't have this, and you would be forced to move to NoSQL, but and yet you can achieve the scalability that you want. So you will no longer have the bottleneck with an in-memory distributed cache. So what does an in-memory distributed cache look like? I'm just giving an NCache example, but this applies to pretty much all in-memory distributed caches. You've got the application tier up here. You can scale it as much as you want. Your database, about 80% of the traffic gets trapped at the caching tier. And this is just an average. Sometimes it's more, sometimes it's less, but that's pretty much you cached. And again, this picture is slightly deceiving. It is implying that you always go through the cache to the database. That's not the case. That is just one model. The other model is that the caching tier stays on the side here, and then you go straight to the database, you get the data, and you cache it. So the next time you want to go to the database, you go check the cache. If it has it, you get it, otherwise you don't. So that's where the cache is on the side. This is when you want to do what we call the read-through model, where you just think the cache is the database. You come to the cache, and cache gets it from the database. I'll go into more detail in that, but I wanted to. So this is the picture, and the reason you don't have this, the reason this solves the problem is because just like the application tier, you can add more servers in the caching tier. Not as many as the application tier, of course. Usually the ratio is about 4 to 1 or 5 to 1. So 4 or 5 servers here to 1 server here with a minimum of 2. So the reason you would want a minimum of 2 is because it's in memory, so you want redundancy. So you don't want the data to be lost in case any one server goes down. Again, scalability is one goal. The other goal is high availability in most cases. If that is not your goal, then you can avoid that. So this is the caching tier. The distributed cache, by nature, pulls the memory of all and the CPU of all the servers in the cluster. So it builds a cluster and pulls the memory and CPU of all the servers together. So as you add more servers, your memory capacity grows, your CPU capacity grows, and that's how you don't become a bottleneck, which is not the case with the relational database. NoSQL also can scale linearly by adding more shards, but that's a separate story. So this is how distributed cache would fit into your environment. Now this is only a logical representation. This cache does not have to be on a separate set of servers. It can be on the same box as the application. Although what we tell customers is if you have more than 2 servers up here, and so if you have 3 or more here, then it's much better to have a separate caching tier. It's a much cleaner deployment strategy because this makes the servers stateless. So there's no data being maintained here. All the data is being either maintained here or here. So that means that you can bring any of these down for maintenance or if it crashes or whatever, and you don't lose any data, which is another thing that happens, especially in case of web applications. I'll talk about that too. So this is what a distributed cache looks like. That's why it solves your scalability problems. Any questions so far?
The more node that we add to our caching tier, is it just for the replication or for both storing the new data and the replication as well?
Actually, there are different topologies in case of NCache. Other products have their own strategy, but in case of NCache, you have partitioning, and then so there are One topology is where you replicate. So the more nodes you add, the more copies you have. But the most common is partitioning. So there are always 2 copies of everything. So data exists in one active and one passive. So even if you have 5 nodes, there's still 2 copies. That means that as you add more nodes here, you're increasing your capacity, not making that many more copies. You can, if you want, that's one of the topologies that we support. In some cases, you do have a need, but in most cases, you just want partitioning with replication so that every partition is on different. So, and I'll talk about that.
You might talk about this further down. I can certainly see how you get the advantage for reading data, but what if your application's writing data goes to the database? How is the cache made aware that write has happened to the database and propagate up to the cache?
Yeah. Very good question, and I will go into that in more detail. But if your cache has the intelligence, it will synchronize itself with the database. NCache does, and you can look at other options whether they do or not. But the cache, because the cache has a copy of your database data, a subset, so this staleness or freshness becomes an important issue. And I'll go into a lot more detail of that. Okay, so what are some of the numbers that you should expect? These are NCache numbers, so you can see whichever solution you're looking at. For example, if you're looking at Redis, you should see this as a kind of a comparison baseline. So with a 2-node cluster, you'll do about 32,000 writes per second, 50,000 reads per second. These are 1K objects with a key, and this is the capacity from the server side. So this is like the 2 servers combined would do about 32,000 reads or writes per second and 50,000 reads per second.
Is it configurable to favor reading over writing? So some applications tend to write more, some tend to read more. Can you balance one against the other 2?
Actually, the topologies will load balance both activities. So if you're doing more reading, your performance will actually be faster because the writing is slower because of the fact that, and actually, these are the numbers when there's also replication happening. If there wasn't any replication, these numbers would actually go up. Let me actually quickly show you the numbers, just a comparison of these. So if I were to go to our website and go to the benchmarks and cache, if you see, these are the numbers I'm showing you here. But this is with the partition and replication. If I turn off replication, I'm doing about 54,000 writes per second and 50,000 reads per second. So the writes are actually faster for some reason than the reads are in case of NCache. But as you can see, the reads and writes are pretty much the same performance, but there's no replication. When you add replication to it, it's about 60% the performance of the reads. And that's with an async replication. When you do a sync replication, which in some cases you do want to, the writes become even slower. So it's instead of 32,000, it's 20,000 writes per second. And with a 3-node, it's 26 instead of 48. But it's still a linear curve. It's just not a very steep slope.
You more sacrifice reliability for.
Yeah, and so most of the time you would not want to do this. You do this only with very, very sensitive data, like financial data.
Yeah, so
but for most other data, you can just live with the async replication.
Sorry.
Okay.
How do you get the write boost? Because surely you're writing to the bottleneck, which is the database. So how can you get more writes out of it?
These do not include the database writes. These are just the cache writes.
Okay.
So the database performance is something that is always slow, and I'll talk about how you can circumvent that with the write behind feature. But whenever you go to the database, you're going to have the same issues. The database performance, again, is not the issue, it's the scalability. So if you have any database, it's super fast if you don't cross that certain threshold of load. But as you go beyond that load, it starts to slow down because it's just 1 or 2 servers. So you can't
really scale. Balancing things. So on the database, you can architect the database to be much more write friendly, so have less indexes and things like that, because the read load is taken off by the cache.
Exactly.
So it's,
And
it's where how the NCache works with those strategies of the indexes and things. Of the
exactly,
database.
exactly. So by having a cache on top of the database, you're taking 80% of the load off of the database. Now the writes are going to be faster because there is not as much competition with reads. Because the writes are going to take the time. You have to update, you have to create indexes. And there are certain requirements that a database has to have. But it's going to be much faster because it's not being overwhelmed. Again, the emphasis is more on scalability. The database, you can optimize it fairly well for a lower load. And you may be able to get away without caching. But as soon as you want to scale, that's where caching comes in, because without this, your database is going to start to choke.
So, I mean, when you're reading from a database, typically you might join across two tables. Are you saying that you can do the join, a SQL-like query?
In case of a cache, yes, the joins are not part of the joins are actually more costly in the cache than in the database, because you have a distributed environment. And but let me come to that. Let me come to that quickly. Okay. So these are the scalability numbers that you should look for. Again, with these numbers, as you can see, you're not going to have. So what you want to do is architect your application so it never has scalability issues, where you just simply can grow in this fashion. Because the really ironic thing about scale, or the lack of scalability, is it hits you when the business is doing really well. So you may be an airline and you run this weekend special to Hawaii, and everybody's logging into your website trying to do flight search, and so they can buy tickets. And guess what? That's where it starts to slow down. Your response times go down to 30 seconds, and people will get frustrated. They move. And then in case of it might even crash, because if you have too much traffic, it's going to start to crash. Ryanair once told us that if their website is down for half an hour, it costs them more than 100,000 euros. So there's a really scalability is something that it's a really important vitamin that you must have, or else you're going to need a lot of paracetamol here now instead of Tylenol. So, you want to architect this correctly from the beginning. Make sure your application is able to take advantage of caching. So there are three ways that caching is used. Number one is application data caching. The word application data means it comes from your database. That's what it says. Although all data is application data, but I'm just going to call this data that exists in your database. These are your customers, your accounts, your reference data. Everything that is coming from your database is your application data. And this is a permanent data. Oops, sorry. I keep confusing the keys here. So it's a permanent data. Permanent again means it sits in the database. It's there forever, technically. And so the nature of the problem is that there are two copies of the data, one in the database and one in the cache. So that's where those types of questions that you asked come up. The second common use case is ASP.NET specific caching, which is also, in case of Java applications, it's web application. ASP.NET specific caching is all, other than even ASP.NET applications will use the application data. So that I'm excluding that from here. But other than the application data, ASP.NET has its own data that it wants to cache. It's sessions, view state, page output. In case of Java, it's also sessions. It could be Spring, which will also do. I see you can do edge caching there also with page output. But there, the issue is that the data exists only in the cache. So you cannot afford to lose that data. In case of application data, you can afford to lose it from the cache, but you can always reload it. Of course, it's costly. It costs performance issues. So most people don't even want that. But in case of transient data, it's detrimental if you lose the data, because it only exists in the cache. The third common use case is something that a lot of people don't know that distributed caching can be used for. and that is to do runtime data sharing. This is like you want to share data across multiple applications or across multiple instances of the same application in a pub/sub manner, in an async manner, so that you don't have to do polling, you don't have to use message queues and other stuff. So that's the third. That's also transient data. It may or may not exist in the database, but it's definitely being shared at runtime. So those are the three common ways that caching is used. And I'll go into at least the first two, and I'll briefly touch the third one because of the time limitation. Any questions up until now? And I am going to cover a lot of detail in this. In fact, I had to cut down because there was not enough time. Okay, so before we get into the caching features, in terms of what the application data caching does, let's go into architecture. And distributed cache runs in your data center. Your application is deployed either in the cloud or what we call on-prem, which is really your data center. So high availability and scalability are both very, very important characteristics. So the architecture has to meet all those goals. Let's first see what are the different components of a distributed cache. And this is true for most reasonably good caches. But NCache, of course, this is coming from NCache. So there's a client portion of the cache, which is you have a client API that gets shipped with your application. You may have some pluggable modules. For example, the session state is a pluggable module. View state is a pluggable module, output cache, and Hibernate, second level cache, is a pluggable module. We have implemented our own entity framework L2 cache, although the entity framework architecture does not really provide us the entity level caching, but we've done an ADO.NET provider. Either way, it's a pluggable module, which means there's no code changes required for your application. So if you're using any of these, or if you want to use a distributed cache for any of these, the good news is there's no programming needed. Just plug it in, test it, and make it live. So you don't have to schedule it into your development schedule, because there's no real integration with it. There's no coding. So that's the client portion. There's a server portion, of course, because it is a cache. It's an in-memory store. So there's a cache cluster, and then there's some server-side code. There's a read-through, write-through, cache loader, and a bunch of other stuff that is your code that you write and you register to run on the cache cluster. There's also, in case of big data, there's a MapReduce code that you have. There's another feature we've implemented called entry processor code, which is your custom code that runs on the cache cluster. So this is a typical breakdown of a cache. And this is the communication between the client and the server is almost always TCP. There's some UDP involved, but only for discovery purposes by some products. NCache doesn't do it. We used to do it, but we realized that it was a lot more efficient just to stick with TCP. And then within the cache cluster, it's all TCP. So there's a native API, which is a .NET assembly of sorts. And in case of NCache, we use Google Protobuf. Has anybody heard of Google Protobuf? So we use that. It's an open source library from Google that packages our API into socket communication packets. And we send that here. We use Google Protobuf to unpack it back into objects. And that's how these two talk. So we're not using any WCF. We're not. Any questions?
Yeah, if you use the pluggable modules, you're not doing any coding, right? How does the server knows how long to maintain the object in the memory? Do you have some sort of mechanism to expire the object, or if you're doing too much write to the cache, would it not,
Good question. Yeah, so when you're doing the pluggable module, all the configuration is through the configuration file. So in case of sessions, you get to specify how long the session is going to stay in the cache through the config. The same is when you do the Hibernate second level cache, there's a section in the config that's NCache specific, which tells Hibernate how long should this object be kept in the cache, expiration wise. Because in case of a pluggable module, you don't have a lot of control. because you're gaining time by not putting the development effort, and you're losing control in response. So because of that, it's all configuration based. But it serves its purpose because a lot of, especially for sessions, there's no other way. I mean, that is the framework that you have to plug in, and that is sufficient to do it all through the config. It's only the object, the application data caching, where you want more control. And I'll go into this in more detail that you really want to do your own programming. If you have time, you want to do your own programming. It gives you a lot more control than just using the pluggable modules. The only time you should use the pluggable modules is when you don't have time, simply. So we don't use any TCF, any WCF, any of that, because it was heavy, and our own socket level communication is a lot more efficient. Many of the other open source caches do the same. App Fabric did not. They used WCF for the communications. And we did benchmarking of this way back, and then we keep doing it. By having our own really optimized socket level protocol, we are very lightweight, and we can, the performance is just much better. And you'll see it when you take a look at it. Okay, so let's go into the internals in terms of the architecture. So the first thing is the cache cluster. The cache cluster has to be dynamic for it to maintain high availability. If it is not highly available, you will have downtime. Let me give you an example. Memcache is very popular cache, right? It does not even have a cluster. So every node is an individual node. The client knows about all of them. So if any node goes down, you're in trouble. So that's where some of the people have developed options where they will do on the server end, they have provided some replacement of that. But a good distributed cache must provide a clustering capability on the cache server side. If the cache that you're using does not build a cluster of servers, you're going to have issues with high availability. In case of NCache, we use peer-to-peer architecture. We actually took JGroups, which is a Java-based group, like a clustering library. Has anybody heard of JGroups? Long time ago. We converted it into Java, into .NET back in 2004-5 time frame, and that's what we have used for our clustering. So it's highly dynamic. We've optimized it quite a bit, and it's a peer-to-peer architecture. That means there's no single point of failure. There's no master. There's no slave. There's no majority rule. Everybody is a peer. So you can add any server at runtime. You can drop any of them, and the cache will continue to work. So that's the real flexibility of having a peer-to-peer architecture. The peer-to-peer architecture is something that is not very common on .NET caches. The only cache that has this is NCache. On the Java side, you do have what they call in-memory data grids, which is the same as just the terminology difference. They do have peer-to-peer architecture. Many of them do. The other aspect is the connection failover. That if any server goes down, all the clients that are connected to it should continue to work. So that should all happen automatically. So the cluster itself should be resilient, should be self-healing. So the word self-healing means that whenever a server goes down, the cluster membership is updated and propagated to the clients. The connection failover means that the clients are able to continue even if a server goes down, because they have the ability to talk to others. They're either already connected to all of them, or they will connect, depending on what the topology is. And I'll go over that in the next slide or two. Dynamic configuration means you don't want to hard code most of the configuration. You want to be able to, of course, they're all stored in the configuration file, but you want to propagate. So for example, what happens if your configuration file said that you only got two servers, and you want to add a third one at runtime? So the clients need to know about this once you've added it, because you don't want to stop your clients. You want to have everything run smoothly. So that's where the dynamic configuration is. Whenever you add it, a new cluster membership is created. I don't know if that slide is there or not. So a new cluster membership is created and propagated to all the clients. The clients will pick it up, and if they need to connect to all the servers in the cluster, they will connect to the new one. If not, they'll keep it in the list, so that if their main server goes down, they'll know that they can connect to this one also. So that's the dynamic configuration part. So the more of that you have, the more your cache will. Caching topologies are essentially ways that a distributed cache stores data, does replication, and manages collection. So those are the three things: stores data, replicates, and manages connections. So in case of NCache, there are 4 topologies. The first is called mirrored cache. It's a 2-node active-passive topology. So there's the active node, there's a passive node. All the clients are connected to the active node here. All the data is in the active node, and a whole copy of it is on the passive node. You know, a typical mirroring, right? So there's an active, there's a passive. And if the active so whatever you update on the active is asynchronously backed up to the passive. That means if the active node goes down, there's a slight chance that you will lose some of the data. If it crashes abruptly, you may not, but there's at least a chance. But once the active node goes down, the passive node automatically becomes active. And all the clients automatically move to the new active with the previously passive node. Because all of that information is kept, is given to the clients. And when I say it's given to the clients, it's not your application. It's the client library. It's the client portion of the cache. And that's how all caches do, depending on whatever their capability is. I think NCache probably has the most on the .NET side. On the Java side, as I said, there are also others. This information is sent to all the clients, and they will connect. So again, everything works smoothly, seamlessly, even if a node goes down. And then if you were to bring this back up, you again, it'll be up. This topology is a low-end topology. People use it when they only have one dedicated cache servers, and they want to maybe make one of their web servers as a backup or the database as the backup node. It's very fast. It's fast for both reading and writing, because the replication is async, so that's why the writing is fast. But the problem is this is not a very scalable topology. You cannot grow to be more than this. Another topology is replicated cache, and that comes to the question that you asked, which is, what if you have more than two servers? Are you going to have more than 2 copies of the data? And in this topology, yes. So in this topology, you have you can have more than 2 servers. Every server is active. What that means is they have the clients are connecting to it, and every client connects only to one server at a time. So and in case of NCache, the clients stay connected. So they don't. It's not like HTTP where you connect and then you disconnect at every request. Here you connect and you stay connected. So every server is active that has its own clients. The more servers you have, the more copies of the cache you have. That means that by adding more servers, you're not really growing the storage capacity. Normally you would want to grow the storage capacity. In this case, you don't. So you just make more copies. There are definitely situations where you want to do this, but here the reads are super fast, of course, because the entire cache is right there. The updates are not as fast because they're synchronous. They have to be synchronous. Why? Because all the nodes are active. That means somebody else could be updating that data on that node. So you want to update item number 3 here. Let's say you are this client. You want to update item number 3. Another client here wants to also update item number 3. Well, who gets to do it first? And they need to be updated in both places or in 4 places. So there's a token-based algorithm to manage concurrency in this topology. So it's not as good for updates as it is for you. Partitioning is the most common. Partition with replica is the most common of all, which is that you have partitioning where you add more servers. The more servers you have, the more partitions you have, and the more storage capacity you have. All that scalability that we talked about. And each partition is also replicated. And again, it's all dynamic. There's a distribution map that gets created at runtime. This is a hash value type of map. It gets propagated to all the clients. So those are the 4 topologies that NCache has. This is our most popular topology. It scales very linearly, and those are the numbers I told you. Any questions so far before I actually go into the application data caching?
So if one server goes down, and then the replication factor is under question mark, so if another servers come up and join the cluster, does it do the replication again on the new server or not?
Yeah. So let's go through it. Let's say that this server goes down. Partition 3 is down and replica 2 is down. What's going to happen is, in this topology, the partitions are active and the replicas are passive. That means the client can only talk to partitions, and the partition talks to their replica. Okay. So this server is down, and replica 3 now becomes active because partition 3 has to be available, right, for it to be highly available. Replica 3 becomes partition 3, but now you have 2 servers and 3 partitions, which is not right. So it will merge itself with partition 1 and 2. Once it does that, then a new replica of a partition 2 will be created here. All of that's going to be done at runtime automatically behind the scenes for you. And similarly, if you add a third node, let's say you only had 2 nodes and you add a third one, a new partition will be created. Then a replica for this has to be created here, and let's say replica 2 was here, that needs to be moved here. So all of that is done behind the scenes. It's done much more intelligently than this. So there's no unnecessary movement of data. It's only the data that you have to move that is moved. But the rebalancing of the partitions and the replicas is done automatically by NCache. That's one of the really nice things about this. Is it's all dynamic. It just happens. You just add a node or drop a node, and it just happens. Any questions? Finally, there's a concept of a client cache, which works with any of those 4 topologies that I mentioned. This is a cache on top of a cache. So this is like a local cache. This could be in proc, right here. So this is like your ASP.NET cache. It's the equivalent of that. The only difference is it's synchronous. It's kept synchronized with this cache. So a local cache, if you had a local cache and you had a 5 or 10 server web forms, those would be 10 different copies of the cache that had nothing to do with each other. That could be so the same data could have different versions in 2 caches, which is a problem. In this case, that wouldn't happen because the client cache will be synchronized. So let's say there's a data item in the client cache, which is also here. Another client goes and updates that data here. So it updates its own cache and updates this. This cluster will notify all the other client caches that have that data, so they can go and update themselves. And because of that, the client cache is synchronized. So there are 2 nice things about client cache. One, it is synchronized, so that way you don't have to worry about the correctness of the cache. Second, that you don't have to do any special programming. It's just a plugin. So you are programming as if you're talking to this cache. So you do your cache.insert, cache.add. You connect to this cache, and through configuration you just plug in a client cache, and that could be either in proc or local out proc. So you want to do a local out proc when you have multiple processes on that box, which is usually the case with an ASP.NET application. You have multiple worker processes, you have multiple app domains. So in that case, it's better to just have a local out proc, especially if that client cache size is large. But if it's not large, then you can even have an in proc, and each process will have its own copy, and they'll all be synchronized, through the cache cluster. So a client cache is a very powerful concept. You must use this. It's a cache on top of a cache. Why do you need a cache? To take the load off of the database. Why do you need the client cache? To take the load off of the client, to take the load off of the cache cluster. Because now suddenly you have cache within the application. This is right there, in proc, or even very close by. And your performance improves. In case of NCache, the in proc, NCache keeps it in an object form. So you don't even have to go through serialization costs anymore. Once it's fetched once. So this is something. But the client cache you should use only when you are doing more reads than writes. So, for example, in case of session state, you do one read and one write for every request. Client cache actually makes things slower because the writes have to be done in two places now, right? There's the client cache and there's the cluster. But the reads, so there's no benefit of having a client cache if you're doing equal number of writes than reads, or if you're doing more writes, then it's actually negative. But most situations you are reading at least 5 to 10 times more than you're writing. So that's where the client cache really helps. Any questions on this? One last thing, and then I'll go into the data caching features that we. If you have a distributed cache, you might have your application deployed on multiple data centers. And just like you're going to have your database replicated, probably, you should also have your cache replicated, especially for transient data. Not the data that exists in the database, because that you can get through the database. But the transient data, for example, sessions or others, should be replicated across. But the WAN becomes a latency issue. So you can't really build a cluster across the WAN easily, because then the performance drops. So that's why there's an async replication that NCache provides. We call it a bridge, an NCache bridge, which does not have to be a separate box. It can be on the same box as this, but just like a logical. It can be on a separate box. And whatever you update in this cache is asynchronously backed up here if it's active-passive. If it's active-active, then it's a two-way synchronization. In case of active-active, NCache will do conflict resolution also. So whichever distributed cache you use, keep this in mind, that if you have multiple data centers, which is now very easy in case of the cloud, Amazon and Azure make it like that you can very quickly create multiple regions in Azure, that you need to understand these, just like you have to tackle the database part. In the database, you might have one single location of the database that both regions are accessing, or you might do the database replication, or you might do partitioning. There are all sorts of strategies. In case of cache, also, you need to have that option. Okay. Any questions up until now before I go into the application data caching?
Go back. This async replication, underneath the mechanism, is it a TCP connection or is it the shared memory?
It's all TCP. It's all TCP. It's a socket.
Not that one, within the one box.
This is also all TCP. This is all TCP. This is just the logical memory that I said. When you add multiple servers, it pulls the memory. So the cache will treat that as one memory, but it's really separate memories across multiple boxes.
Within a one box, why can't you use the shared memory? It's not possible.
Within the same box, you could, but again, this is a cluster of multiple boxes. That's why you need to. So think of it this way, right here. So these are your multiple boxes. So partition 1, partition 2, partition 3. So this is logically, the entire cache is broken up into 3 partitions.
Yeah, but if you go to 19, next slide, 19, where we're saying even it's an in proc.
The in proc is only in case of the
In this
client cache.
In that case, it's also running on the same box, isn't it?
Yes. So the client cache is on the same box.
And then it's communicating with your other process on the same box in the TCP mechanism.
No, actually, good question. So if it is out proc, .NET automatically optimizes the TCP communication not to go through the sockets, but to use, I think, forgot. I think it is. I think it does use shared memory. So if you have a local out proc cache, that means it's a separate process, and you've got multiple processes here. So that communication is optimized. Yes, it is. I just don't know it on top of my head. Okay, so when you're caching, here's what a typical caching application looks like. Very simplified, of course. You create, so you want to load a customer based on some customer ID. You first want to check the cache. If the cache has it, then you don't go to the database. Otherwise, you go to the database. So if you first construct a key, and the key in case of NCache is all string-based. Other caches, I think most caches use string-based keys. But the key usually should have some sort of a type information. So this is the type customers, the attribute customer ID, and then the actual value. So that's one way to format a key. So you use that key and you say, is it key? Is this object in the cache? If it's not, then go and get it from the database and put it in the cache. So when you put it in the cache, the next time, of course, you will find it. So the next time you come to this method, it's not going to go to the database. This is the method where the cache is kept on the side. Where the cache is on the side and you're going to the database, but before going, you're checking.
What happens if you get another client who's updated their customer? This data is going to be stolen.
No, because if you go back to this, it depends whether you're getting it from the client cache or from the custard cache. Again, this might look like it's ASP.NET or system.runtime.caching type of a cache, but it's really either this cluster or it's a client cache, in which case it's again kept synchronized. In a client cache also, there's a technical possibility that you might get stale data. If that is the case, there's a mode called pessimistic sync, where it will ensure that you'll never get a stale data. It has one extra trip, because it checks the cache cluster and says, do you have a new version of this data? If not, then it takes it from the client cache. So it slows you down slightly, but not as much. But that's the whole idea, is when you use the cache, use it with confidence that you are not going to get stale data.
Question. So is the insertion of the key to the cache, is that done synchronously or asynchronously?
It can be done either way. So that's a synchronous call. That means you will block here until the cache is updated. But there's an insert async call, which will give you control back immediately, and the cache update will be done asynchronously. In which case you can specify a callback, which will be called in case something goes wrong.
So it very much depends on the actual time that would take to actually load the data or repeat the data from your database, right? Because your server to your actual application server to the cache communication might be very expensive.
Actually, it is faster than the database. It's about 10 times faster. It's all in memory. It's key value based. The only cost in this is the serialization cost. I mean, the only significant cost. Of course, there's always cost, but when you're going from here to here, it's because it's a key value. There's no.
Is the communication, is that an open communication? Is the channel always open?
It's always open.
Okay.
It's always open. So you're always connected. So you basically, let me just quickly show you. Here's the API. Good. So you connect to the cache, and every cache is named. You connect to the cache, and here's your cache handle. So you keep that cache handle throughout your application, and you use that. At the end of the application, at the end of when you're done using the cache, you see cache.dispose, and that disconnects you from the cache. So that's how you're always connected, and you get there very, very fast. The typical performance is sub-millisecond, so it's very fast. As I said, if you go back here, right here, these are some pretty good numbers. To be able to do 48,000 writes per second, pretty much. It requires the cache to be very fast. Okay. Any questions on this? Okay. So here's the API. API looks very straightforward. Looks a lot like the system.runtime.caching API, which used to be the ASP.NET Cache API, although and we intentionally kept it very similar to that, although it's a superset because we have a lot more features than they do. But the basic use of the cache, there's a cache.get, there's an index operator to do the get, there's an add. The add will add, insert is basically, insert will either add or update. So if the item already exists, it updates it. If not, it'll add it. So you use insert if you always want to add, either add or update. If you want to get an exception back if the item already exists, you do the add. Again, this is the same as ASP.NET Cache object. Then of course the remove. So this looks very straightforward API, and this is another benefit of using the cache is that if you use the read through write through mechanism for that data which can be fetched through the cache, you simplify everybody else's programming effort, because it's much simpler to do this than to do ADO.NET programming. Because of course in some cases you have to, but whenever you can, stick to the cache. Okay, so what time is it right now?
It's almost 7. 5 to 7.
5 to 7. I'm running late. Application data caching, you asked the question. The most important thing is to keep the data fresh. Why? Because that data exists in the database and also in the cache. The two places where the data exists. And unlike the cache, where you can synchronize, the database is an independent entity. So there has to be different ways that you want to make sure this stays correct. So, for example, the first and the most common is expirations. With permanent data, you use absolute expirations. You say, okay, I think this data is good for 10 minutes, or for 1 minute, or for 30 seconds, or for whatever. I don't think anybody's going to update it in the database for that long, so let's just expire this after this long. In case of transient data, there is no database, so you want to expire because you no longer need it. Sessions. The user has logged out, so that's no longer needed, so expire this. So this is sliding expiration, which is basically expire on inactivity. When nobody is touching that item, either reading or writing it, expire that. So transient data is usually expired with a sliding expiration. Permanent data is absolute expiration. There's also a difference between reference data and transactional data. For example, your lookup tables, your product catalog, those are your reference data. Your customers, your accounts, your activities, those are your transactional data. Transactional data is something that you update very frequently, that is created at runtime and is updated over and over again. Reference data is something that it's not read-only, but it is not changing very frequently. So those two need to be managed differently for you through expiration. For example, the reference data would expire probably every few hours, or maybe once a day, or once a week, whatever. But the transactional data, most common expiration is like 5 minutes. But some customers expire this every 30 seconds. Because in that 30 seconds, they'll read it 5 times. And that is good enough. So that's one way to keep the data fresh, is just to remove, But the second is to synchronize the cache with the database. And there are 3 different ways to do that. You would do this when you have other applications that might be updating the database. So your application is one that is updating the database. And there are other applications that are also updating the database. And they don't have access to the cache. This could be a third-party application, some legacy application, whatever. This could be somebody who's just run a batch script to go and update something in the database. In that case, what do you do with the cache? So you need to be able to synchronize. So NCache, for example, gives you a SQL dependency as a feature of ADO.NET. As you know. So we use SQL dependency, which is there's also an Oracle dependency. And then we've got our own DB dependency, which is based on polling. So there are 3 different ways: SQL, Oracle, and DB, and there's also the CLR procedures. So this is good when you're also adding data to the database and you want that to be added to the cache. Why not have a CLR procedure? I'm just going to sit a little bit, go back problem. Second. Sorry about this. So CLR procedures is your code running within the database, called from maybe a trigger or some sort, and it goes and adds that data or updates that data in the cache. Especially if you want to add data to the cache as you're adding to the database, that's an excellent way to do that. But for that to happen, your cache has to allow you to be able to call the cache from the CLR procedures. And that's where the async, I think you had asked, somebody has asked for the async calls. If you don't have async calls, the database transactions will become really, really slow because you're going to the cache cluster and update and all that other stuff. So it's good to do an async update of the cache. So that way the trigger will immediately go back and the database transaction will complete, because the cache is really not going to fail. The database transactions fail not because the database crashes, it's because of data integrity issues. You have check constraints, you have referential integrity issues. None of those exist in the cache. The only time cache fails is when there's an actual problem. So those are three ways that you want to synchronize. Now, if your application is the only application dealing with this database, it can always update the cache. So you don't need to use this feature in that case. But it's a very powerful feature. A lot of our customers use it. It gives them total control. This is the biggest fear of using a cache in a real business situation, which is what's going to happen to my data. Is my customer going to withdraw that $1 million twice, or not? So that's the issue. Of course, you want to be able to synchronize the cache not only with the database but through other non-relational sources. For example, you may have data in some third-party system, and you can use a file as a sort of a synchronization flag thing. Or you may have a custom, you may have a web method call through which you can check if the data has changed or not. So there are other ways that you can synchronize the cache with other data. Because especially if your data is on a mainframe, you really can't use these. But you may be able to use a custom dependency feature, which is your code that makes a call into that system. So this may be called every 15 seconds. And so your custom dependency is called every 15 seconds, let's say. And it calls that legacy system, says, is this data changed? Based on that key, because the custom dependency is your code that is registered against a key. So based on the key, it knows which data to look for, and if that data is changed, it'll what we call fire that dependency and say, yes, this has changed. So now the cache will go ahead and remove that data from the cache. NCache would, at least. So you want to be able to synchronize the cache with your databases or your data sources. Another thing is to maintain data integrity is there's certain data where you have a customer, maybe you have a collection of orders. What if you remove the customer from the cache? Are you really deleting the customer from the database, or is it really only removing the cache? I mean, customer you're probably not going to, but I'm just saying one-to-many or one-to-one. So it's always safe to say, well, since the order is dependent on the customer, there is no order without a customer. So if the customer is being removed, might as well remove the orders from the cache. So that's where the cache dependency feature. Cache dependency is also a feature that comes from ASP.NET Cache. So we've also implemented that. And that means the NCache or the cache, the distributed cache will manage all of this for you. So your application does not have to keep track of it. So that's, as you can see, is a very comprehensive set of features to make sure that you can synchronize the cache with your data. So any questions?
I have a question. With the DB dependency, what's the performance hit on that as you scale up? If you have hundreds of dependencies, because it'll be hitting the database, right?
Actually, this is faster than this. because in case of SQL dependency, for every item there's a separate dependency created. So that's additional data structures in the database. And the database will use its own database notification mechanism. So if you have, let's say, 100,000 items and 10,000 of them change, there's 10,000 events flying back, which is a lot more chatty and has a performance overhead. Then a DB dependency, which is after 15 seconds, let's say, it's going to go and issue a SQL statement. It could be even a stored procedure, which will say, okay, let's check which of these, because there's a special table that gets created, which is a sync table, which has a flag concept. It says, give me all the rows where this flag is true, or something. I think it's either a flag or a number. And then you'll get back only those 10,000 in one fetch. So it's actually more efficient. It's not as real time as these, but it is. But if you can wait 15 seconds, then DB dependency is actually a better strategy. If you cannot wait 15 seconds, if you really want to do it immediately, then SQL dependency. And even more efficient is a CLR procedure, which is you initiate this from the database.
Is there a more configurable way of sort of invalidating a cache? So based on the memory, you've got keys. So could you say invalidate? Say you have, say you've added an extra column or extra property to something, so that to I know your product or all your products. So you want to invalidate all products and now on get them differentiated cache for all products. Can you do it based on a pattern or more?
Yes, at least NCache has it. It depends on the cache. So this is the first part. The second part is how do you find data? So for example, if you had all those keys, you could do a bulk get here, and then or just a bulk remove. So in one call you can remove it.
Yeah, just invalidate.
Or you could issue a SQL or a link query and say, give me all the customers where the customer.city is London. You may have, I know, 100,000 customers and only 5,000 of them are in London, or 500 of them are in London. So with that query, you can issue a query and say delete these customers also, where customer.city is equal to New York. Just like in a database, you can issue a delete statement. You can also issue a delete statement, at least in an NCache. At the minimum, you can do a fetch. It'll give you all the keys or all the keys and the values, and then you can take those keys and say bulk remove. So that's one way. So there are multiple ways. One is if you know the keys already, just issue that. The second is you can just issue a delete statement with a criteria, and then it's just going to go ahead and delete all those. Or third is you fetch them all, and then whatever inspection you have to do, based on that you can say take these keys and do a bulk remove. There are also other ways. For example, there's a data grouping feature where you can group and subgroup. So you can say delete this entire group. You know. There's also tags feature. There's name tags. All of these you can include either you can. There are special API calls that you can call for them, or you can just issue them within as part of the SQL statement. So you can say select customers where customer.city is London and customer.group is not so important. Whatever, you know. Or customer.tag is this. So
those tags would only exist in the cache.
These are the tags that you have specified when you're adding the item. So when you add, you also attach this as metadata. So you say these are. So this item has these 4 tags. And those tags could also be used on other items. So it's like a many-to-many between tags and items. And then later on, you can fetch items based on tags.
Tags are only used by the cache. They don't actually store in the database.
No, yeah, they're only in the cache. Yes, yes. So that's a cache level metadata.
Yes, that.
And name tags are the same as tags, except they have a key and value. So every tag has a name and a value. So sometimes you need to do that. For example, you've got plain text. You're caching text, but maybe it's XML or something, and you want to be able to search on certain tags within that text. In case of objects, NCache will automatically index them for this. So NCache has an indexing feature where it'll take the attributes of these that you specify, and so you create indices and say, I want to index customer object on the city attribute, or I want to index this object on these attributes. But if it's plain text, there is no attributes. So that's where you can specify name tags at runtime. So they become those attributes basically. So the name is the attribute name and the value is whatever. So the same name can have multiple values. Finding data is important. A lot of the caches, they only give you key-based access. But a cache is a lot more than just key value. Even though it's stored as key value, you're storing objects. That is data. These are your entities, your domain objects. They have come from your database. So although you cannot do as sophisticated of searches as a database, because for example, you can't do joins, because joins are very complicated. You have a distributed environment, and to do a join in a distributed actually slows things down. So the benefit of performance is no longer there. So that's why it's not even implemented. But there are other ways that you can do those things by caching data in a certain way. But you need to be able to search data. And these queries are parallel. So whichever cache is provided, in case of NCache for sure, but because it's a distributed cache, so the same query is sent to all of them, and they all give back their answers, and then you make a union of them, and then you give it back to the client makes a union of them and gives back to the application. So keeping cache fresh is the first part. Finding data is the second part, and grouping is the third part. Fourth part is the read-through, write-through. So this is your code that you implement and register with the cache. This is server-side code. It actually runs on the cache servers, the cache cluster. And you need this code when let's say you're doing a cache.get, and that item is not in the cache. You can ask the cache to go and read it for you if you've implemented a read-through. So read-through is really powerful mechanism. You don't use it for everything, but you use it for a lot of stuff. Some of the benefits are, for example, you're doing read-through, and you want to automatically reload things on expirations. So let's say you've got a product catalog and you think that the price will change every day.